All right, so welcome everybody. So to the third talk of Jayadev Athreya's series of talks in this Infosys Chandrasekharan Colloquium series. And so he'll continue his talk on variance estimates for geometric counting problems. Please go ahead.
Thanks, Anish. Thanks everyone for coming, and appreciate again the opportunity to give 3 lectures. So in the second talk, we concluded rather quickly. We had a discussion about what were translation surfaces and what the counting problem was. We're counting these objects called saddle connections, and we talked a little bit about, very briefly, what the measure was, Veitch's result on what that this counting function, this f hat, is integrable. It's an L1 of this moduli space of translation surfaces, and that you could actually compute the integral. And then, briefly mentioned at the end, the result that I proved with Cheung and Masur, that not only does this thing have finite expectation, it has finite second moment, that it has finite variance. But I want to do a little, since I went very fast at the end talking about that, I want to spend a little bit of time talking about Veitch's result, and then a little bit of time talking about our result and how they work. So again, let's go back very quickly and think about, what is a translation surface? What's the measure? And what is this counting problem? And then sketch a proof of Veitch's result, and then briefly talk about our result. And then that'll take about the first, hopefully 20 minutes of the talk. And then the last half an hour of the talk, I'm going to talk about another moduli space of geometric structures on surfaces, maybe somewhat more natural in some sense. It's going to be the space of hyperbolic structures. We're going to talk about how to put a measure on that space, and we'll talk about a counting problem on that space of counting simple closed curves of a certain hyperbolic length. And then we'll talk about an L2 problem related to that. Okay, so let's go back and let's remember what a translation surface is. So there were 3, I gave sort of 3 equivalent definitions. One was we had polygon or family of polygons in the plane with parallel sides identified by translation. So for instance, you could have something like this, where the identifications are as follows. This corresponds to actually a genus 2 surface with one singular point of angle 6 pi. That a singular point of angle 6 pi corresponds to this corner here, and all of those 8 corners end up collapsing to that one point. If you trace out what the interior angle is, you will get 6 pi there. So that's one thing of a translation surface. 2 is, notice from this definition, you're gluing everything with the translation, so you get a Riemann surface structure, but then you also get a one-form dz, basically coming from dz, d of, so here the observation is that d of z plus c is dz. And so you get a Riemann surface and a holomorphic one form just coming from this identification, and then the zeros of omega correspond to singularities of the flat metric, and more precisely, a 0 of order k corresponds to point with angle 2 pi times k plus 1. And then there's this third definition, which is atlas of charts away from finite set of points, to see transition maps are translations. Are translations. And it's easy to see, for instance, from either of the first 2 definitions, how you get something in the third. For instance, in the first, from the first definition, let's say, what's the chart around this point? Well, you just sort of look at the Euclidean structure around that point. What's the chart around this point? Well, you take this half disk, and this half disk, that would be a very nice chart around that point. The only point you have trouble defining a chart around is a singular point, the red point. I do want to briefly mention, to go between 2 and 3, a key observation, right, is that suppose I have my Riemann surface x omega, and I have a p0 in the surface, which is where omega is non-zero. So omega p0 is not well defined as a value, but you can at least talk about whether it's 0 or non-zero. So it's a non-singular point, and then the chart near there, I could define z of p to be the integral from p0 to p of omega. So just integrate what omega is, and this is a complex number. And so in these local coordinates, omega is just dz. So this is how you build an atlas of charts from definition 2. So this is going from definition 2 to definition 3. And then going back from definition 3 to definition 1 or definition 2, you have to, definition 3, for instance, to definition 2, you pull back dz from C, and then you have to check, okay, well, what's happening at these points that I didn't have the chart around? You have to be a little bit careful there. So there's some work to be done, but let me skip that work for now. Okay, and then we had, for instance, so let me actually, for instance, if I have this L-shaped table, that's certainly a nice table, but so is, for instance, so would something, let's say like this, be a perfectly reasonable L-shaped table. So for instance, that's also a perfectly reasonable L-shaped table. And now my gluings would be here and here. Those are not quite the same length. Let me make those a little bit more looking like the same length. Let's say, yeah, those are roughly the same. Those are the same length now. These are the same length, and these are the same length. So as soon as you have 4 parallel sides of the same length, so you can think of both of these points as there's a way of giving coordinates, so local coordinates on the space of translation surfaces with fixed sort of combinatorial data is just sort of given by R2 to some power. Let me write down what this power is. It's R2 to the 2g plus k minus 1. What's 2g plus k minus 1 here? So g is genus, and k is number of zeros of omega. In fact, so let's say when I say that I specify the combinatorial data, what I'm really specifying is alpha, or summation alpha I is 2g minus 2. This is an integer partition of 2g minus 2. And so this 2g plus k minus 1 is, in fact, it's 2g plus k minus 1 is the dimension of homology of the surface rel the k singular points, or the k marked points, singular points. And so what I'm doing is I'm essentially cutting up the surface into disks, but they're more than disks. They're disks with these points on the boundary, these k points, so they're kind of polygons. And so if I were to take a basis for homology, that would cut the surface up into these polygons, and then my local coordinates are actually just integrating omega along a basis for homology. So that is, I have maybe I have some basis for homology. I'll say A1 through AG, B1 through BG, say R1 up to RK minus 1, so fix a basis, and then omega goes to integral of omega over AI, integral of omega over BJ, integral of omega over R, let's say L, where these L, I, J, K, this is shorthand for I consider all of the AIs, I consider all of the BJs, and I consider all of the RLs here, right? So this is a vector in, if you like, C to the 2G plus K minus 1. That is, I view omega as an element of relative cohomology. And then relative cohomology of the surface. So those are my local coordinates. And then I have Lebesgue measure in these local coordinates. And then what I'm going to do is, since there's a natural kind of thing you can do to these surfaces, which is scaling them. I'm going to consider, so this is a local coordinates gives me, let's say, a measure on the space H of alpha, which I'm just going to call H for right now. I'm being slightly sloppy here. I should actually mention that really what I'm going to do is I'm going to consider one connected component of these, what are called these sort of strata. And I should mention that actually it's quite a difficult result. Kontsevich and Zorich prove there's less than or equal to 3 connected components. They find a series of discrete invariants, spin invariants. Most of the time there's one, but I'm going to elide this difference and just say that we're working with one connected component. Quite any questions / objections, or anybody want to say anything about connected components? Please let me know. Okay. So we have Lebesgue measure, but of course that's going to be pretty clearly going to be infinite because you have this kind of scaling. You can scale anything. So what we're going to do is we're going to consider the subset H1 in H, which is area 1 surfaces. And so here area of a surface is just integral is omega wedge omega bar, or it's just the Euclidean area of the polygon. So integrated over X, that's the area. It's a quadratic form, right? You scale the surface, the area scales by t squared. We're in 2 dimensions here. And then we do a very similar construction that we did to build Haar measure on SLNR. So here is H, here is H1. And then let's say if we wanted to figure out the measure of some set here, we consider the measure of the cone. So this measure is called often it's called the Masur-Veach. It should also probably, Smiley's name should also be mentioned in this context. But Masur is co-author and a friend, and he doesn't like this name. He prefers to call it Lebesgue measure. So let's call it Masur-Veach measure or Lebesgue measure. I'll probably use those phrases interchangeably. So what's true about this, right? There's a deep theorem of Masur and independently of Veach, and in some cases it's actually Masur-Smiley, that the total mass mu, so let's call this measure mu, of H1 is finite. And moreover, and this is going to be crucial for our purposes, so there's an SL2R action on H1. It comes from a GL plus 2R action on H. This just comes from linear action on the polygons. So that would be, let's say, in definition 1, if you want to think about definition 1 of a translation surface. Or you could think about it as linear, R linear, not C linear, R linear post-composition with charts, if you want to think about definition 3, which is this atlas of charts of a translation surface. Or if you like to think about definition 2, where you have a holomorphic 1 form, take the charts you get, post-compose with R linearly post-compose, now you'll get a new Riemann surface structure and a new holomorphic 1 form. So that's a little bit more complicated to say it that way. So it's easiest to see this in definitions 1 and 3. It's literally, for example, let's take, for instance, my favorite, let's say 3 square L, and let's hit it with, oh, I don't know, 2,0,0,1/2. So now what's going to happen is the horizontal is going to stretch. So it was 2 across before, now it'll be 4 across, but it'll only be 1, 2, 3, 4, kind of a half down. And then the top, which was 1 across, it will look like that, right? So this new surface will be, again, it'll be a perfectly nice surface, It'll just be kind of the aspect ratio of all the rectangles has changed. That made it up. If you were to shear this guy, you could do, let's say 1, 1/2, 0, 1. Let's see if I can draw this on the fly. Applied to the same fellow here would be, okay, so I start from here, I go halfway up, go across, go halfway up, go across, go halfway up, and then similarly, right? So that would equal this. So it really is just a naive linear action. And so more than Masur and Veitch's results, the measure is finite. The crucial point is, so maybe a revised version of the statement is mu is SL2R invariant. That's actually not very hard to see. SL2R, this SL2R action preserves the area of surfaces, and so mu is SL2R invariant on H1. That's because Lebesgue measure is SL2R invariant on R to the whatever you prefer, right? On R to the 2G because it's acting diagonally here, and ergodic. That's kind of the crucial part of this result. That's Masur and Veitch independently, and mu of H1 is finite. So this gives me, so whenever I say, now I'm going to say the words random translation surface a lot, what I mean is random chosen according to this measure. And I'm going to normalize it now to be a probability measure. Mu chosen, surface sampled from H with respect to the measure mu. Okay. Okay. Questions? So in particular, I'm not going to spend a lot of time discussing. There are now there's lots of other interesting measures. In particular, the SL2R invariant measures have been classified as maybe the wrong word, but there's some important properties have been found by Eskin Rizakani and Eskin Rizakani Mohammadi that the SL2R invariant measures are all algebraic in an appropriate sense. So there's a version of kind of Ratner's results on homogeneous spaces here. And you could ask a lot of the questions I'm asking now for the standard kind of Lebesgue measure for measures on these algebraic subsets. And that's very interesting, but that's not what I'm going to sort of spend my time talking about today. So now let's go back to our counting problem. So we have this idea of a saddle connection. A saddle connection was a geodesic in the flat metric on X omega, connecting zeros with none in its interior. That is, it's kind of it's a geodesic map. Let's say gamma. Let's say from 0 t, where t is going to be the length. I'm going to parameterize this by arc length to my surface X omega with gamma of 0, with omega of gamma of 0 equals omega of gamma of t is equal to 0. Omega gamma of s is not equal to 0 for every s in the open interval, and I want this to be a geodesic embedding. Okay. It's automatically an embedding once you ask it to be a geodesic, because once you pick a direction here, you're not allowed to change directions, and so you can't actually intersect yourself. Okay. And then we say the holonomy vector z gamma of a saddle connection is, we keep track of how far it goes horizontally and how far it goes vertically. So for instance, I'm going to draw you a couple of different saddle connections on here and tell you what their holonomy vectors are. So let's make the surface not actually area 1. Let's make it, we're just for the ease of computation, all the sides are going to have length 1. And so here's a saddle connection, for instance. Let's call that gamma 0. And z gamma 0 is just 1 plus I. I'll write it in kind of complex notation. Here's another saddle connection. Let's say I go a third of the way up there, 2/3 now, and then I come back here and I go all the way. That's another saddle connection. Let's call that gamma 1. And z gamma 1 is, well, I went across 3 times, and each time going across cost me 2, so it's a total of 6, and I only climbed 1. So that's 6 plus I, and then let me draw you one more. Maybe I go halfway across there, and then I come down here, and I go halfway across, and then I go like that. Okay. So this would be this pink guy, let's call this gamma 2. Z gamma 2 will be, well, I went across 1 and I went up 4. 1 plus 4i. So this is how you build the holonomy vectors. And notice the length of the holonomy vector is the length of the Fowler connection, right? That's so the length of gamma is just the absolute value of Z gamma. In some sense, that's almost a definition. And then we define lambda omega to be the set of Z gamma, gamma saddle connection on X omega. This is a subset of C. It's discrete. If you take, I'm here working only with compact surfaces. It's a discrete set and finite type. And so the question you can ask is, for instance, a natural counting problem is, what is lambda omega? What is the cardinality of that? Let's call that n of omega r. What does n of omega r behave like? This is a natural kind of question if you like dynamical systems. You can think about the dynamical systems on the surface of these linear flows. What does finite type mean here? It means, let's say, finite genus, if you want to think about it that way. And I don't want to have, for instance, there's certain types of degenerations I don't want to allow. But just if you think about X being a compact Riemann surface, that's fine. That's all you really need. Compact Riemann surface of genus G. That's just fine here. I want to avoid things that are called like Loch Ness monsters and so on. But if you don't know what that means, don't worry about it. Okay. So now very much in analogy to the space of lattices, Veach defined. So if we start with a bounded compactly supported function on C, we define f hat on H, but really we're going to think about it on H1 as f hat of omega is summation over Z in lambda omega of f of Z. So e.g., if I take the indicator function of the ball of radius r hat at omega, that is exactly the counting problem I cared about, counting saddle connections. And now, just in analogy to the Siegel formula in the space of lattices, we have Veach's beautiful, beautiful formula. So Veach, says f hat is an L1 of H1 mu, and the integral of f hat d mu H1 is equal to, there's a constant, I'm just going to call it C sub H, or C, it could be C alpha, integral of f of Z dz over C. So, for instance, the number of points in any set is proportional. The expected number of points expected number of saddle connections, which have holonomy vectors in a given set in C, is proportional to the area of that set. This proportionality constant is called a Siegel-Veach constant. These are very, very important numbers. And unsurprisingly, just like in the lattice case, they are related to kind of the intrinsic volume, depending on if you nail down a normalization and you want to say, what is the volume of space of translation surfaces? These Siegel-Veach constants allow you to read off a lot of that information. They are powers of pi times rational numbers. And there's been a lot of recent really beautiful work in terms of computing what these numbers are. Okay.
Jayadev, can I ask a quick question?
Yes, of course. Yes.
So in the semi-simple group case, there's this Tamagawa number formula for the volumes.
Yeah.
So is there any similar global picture here, or is there no such thing that can?
That's something that I think a lot of people would like to kind of understand. I think it's a little bit harder because, I don't know even if we have a really good, definition of, let's say, the stack of, if you consider, say, curves over let's say a field which is a different completion of Q, but then you really want to be looking at the algebraic closure of that object, because right here we're looking at all curves defined over C and then the sections of the canonical bundle. So here's what you'd have to do: is you'd have to define some kind of appropriate notion of measure over the set of curves defined over the algebraic closure of, let's say, QP. And then you'd have to define a space of one forms, a measure, and then you want to say that the product of all these things is some number, right?
Right.
And I think, that seems plausible that one ought to be able to do it, but it seems also that there would have to be a lot of care in correctly defining what all these objects are. And I think the game would be in making all these definitions kind of the right definition. I think it's actually an absolutely fabulous question. I just don't necessarily know how to do it.
Okay, thanks.
Yeah, no, I think there's actually an ambitious program that you've outlined essentially there. Okay, so, all right, so let me mention now very briefly that if you assume F hat is an L1, that it's a slightly harder part of Veitch's result, and we know that mu, and of course we know that mu is SL2 invariant. To prove the second part of Veitch's result is not so hard, because F goes to the integral of F hat d mu over H is now an SL2R invariant linear functional on CC of, or let's say, bounded compactly supported functions on C. So it has to come from integration against some SL2R invariant measure. But again, there's only two SL2R acts transitively on C, which is R2, or C minus 0. And so this has to be some constant times the integral of F dz over C, really C minus 0 plus some delta measure at 0, but you can kind of, yes, you can't see my screen, can you? Right, I'm writing something. Let me stop and resume the share. There we go. Better?
Yes.
Excellent. Okay, so now what we're going to do is so we have this L1 formula. So now the question is, is F hat square integrable? Or in fact, how far out does the integrability go? So I should own up. There's a paper by myself and John Chaika where we're studying a different problem. We're studying a problem about the distribution of angles of these saddle connections. And in it, towards the end of the paper, we make a claim. So we claimed incorrectly that F hat is not in L2. We claimed that. But I should be very clear, that claim is wrong. Our proof of that claim, and this was pointed out to us by Masur, was that F hat, what we actually showed is that F hat is not an L3. We were estimating the tail behavior of F hat. And I should just say, essentially what we were doing is we were observing if you had a cylinder sitting in the surface, maybe a sort of this rectangle with opposite sides identified, that was maybe very narrow, say length, let's say epsilon, then what you could do, and you had sort of zeros on the end of this thing, you could keep twisting around the core curve of the cylinder, and you could generate a lot of curves. Let's say this was a fixed length, this was a length and a half. You could, this picture allowed you to generate a lot of curves of length less than or equal to 1. Basically, you could get curves that looked like, so if you had sort of 1/2 0, you could get sort of 1/2 k times epsilon for this. And So you have this 1/2 k times epsilon. Sorry, that's very sloppy writing. And the idea that we thought is that, okay, well, there's this only one curve that we're trying to specify the length of, this curve epsilon. So that gives me just an epsilon squared worth of measure. So this was saying we thought we were producing sort of 1/epsilon curves, and the measure of the set of surfaces that had 1/epsilon curves was bounded below by epsilon squared. Now, let's play a little game, right? For probabilists in the audience are nodding along, saying, okay, yeah, that would definitely prove that you're not an L2, because if you have a random variable with, let's say, where the probability that you're bigger than t behaves like, say, 1/t squared, then you're not going to get finite variance. But our mistake was that this collection of surfaces which have a picture like this, actually has measure epsilon cubed, because you actually have to decide the initial kind of relative twisting of the curve of length epsilon versus the curve of length 1/2. So it's not just you have to get to freely pick where the curve of length epsilon is. There's also another parameter of size epsilon. So this actually gives you a set of surfaces of measure epsilon cubed rather than epsilon squared, which proves that it's not an L3. It doesn't prove that it's not an L2. It's good that we couldn't prove that it's not an L2, because subsequently, inspired by these discussions, Cheung, Masur, and I prove that in fact f hat is in L2 of H1 mu. In fact, we proved that it's in, we actually get, depending on the strata, we get 2 plus some actual number here, a number which is, it's not getting close to 3. I'm not claiming that our number here is optimal. We get some function of the genus up here. I don't claim that what we get is actually optimal, but we do get a little bit more than just L2. One might suspect that it's actually an L3 minus epsilon. That's an interesting question to me. And I think it's worth thinking about whether f hat is an L3 minus epsilon. Before I sort of talk very, very, very briefly about the proof of this result, very, very briefly, because I do want to mention the last collection of results on hyperbolic surfaces. Let me just mention a couple of corollaries. So in an appendix to this paper, myself and René Rohr use this to get error estimates in almost everywhere counting for the problem of counting the number of saddle connections n of omega r. So I should mention that Eskin Masur proved that n of omega r over pi r squared actually converges to that constant ch for almost every omega, and this is using kind of ergodic theory. And myself and René Rohr get error estimates in this count just using L2. These are not quite as good as the best error estimates, which were obtained by Amos Neveu, René Rohr, and Barak Weiss, but they obtained them in kind of they obtained them using very difficult dynamical techniques, using the exponential mixing of tychology geodesic flow. Our result, in some sense, just uses this kind of relatively easy L2 estimate. But the trade-off is we get the same kind of order of term, but our estimate only holds along lacunary sequences. We have to use a kind of Borel-Tantelli lemma. We use concentration inequality. We say that the probability that you're far away from the right amount is small, and then we use the Borel-Tantelli lemma to add up these probabilities. But we really do need to work along a kind of a relatively well spread out sequence. Again, the probabilists in the room are kind of nodding along because, oh yeah, of course, you have some L2 estimate, you can get estimates on the error terms in these kinds of counts. Okay, very, very brief remark on the proof. So the proof really just relies on the following thing. We start with just f to be, let's say, the indicator function of the ball of radius 1. We prove that is in L2. f hat of that is an L2, and we do that by we need to estimate the measure of the set of omega such that lambda omega intersect via 0, 1. So that is, you have maybe a lot of saddle connections in there. It's bigger than some k. And we want to say that, if, okay, so this is summable is L1, but we need more than just it's summable, right? We need to estimate, that so the function we really care about is this. We want that to be summable. That is, we want in K, we need this thing to be summable in K. Need this to be summable in K. And so we need to estimate the measure of this collection of sets. And exactly what we need to do is what we do is we identify kind of the big contributors to this set via sort of flat geometry of the surface. So we actually analyze the surface and we say, look, what are the possibilities of getting a lot of short saddle connections or a lot of not too long saddle connections? And a key, a key idea is in some sense that this picture of this cylinder is one that can contribute a lot, but we can kind of control the measure of that very easily. Maybe a key idea also is that there is a beautiful decomposition of the surface, which is, I should say, due to kind of Khosrow-Rafi. So I really should mention Khosrow-Rafi's name here. Khosrow-Rafi, and then this is also explained nicely in Eskin, Kuntsevich, Zorich, but really it is an idea of Rafi, which is that every translation surface can be decomposed into sort of surfaces which are all at their own scale. So I'm drawing this kind of scaled picture, but each surface is kind of fat at its own scale. That is, all the lengths of the saddle connections are kind of comparable on each surface. And then there's some saddle connections that help you connect the surfaces that may be kind of shorter. But the key point is the big contribution for us is always going to kind of come from the smallest surfaces in this Rafi decomposition. So actually not even that second one, it's just really that first, that really tiny surface. And then you have to control the collection of saddle connections that cross between these surfaces and say that that isn't kind of an enormous amount of saddle connections. So that's kind of the game here. There's a lot of interesting things that end up coming into it, including some work in sort of computational geometry. A key thing we use is the Delaunay triangulation of the surface and estimating lengths of saddle connections of the surface by sort of combinatorial lengths in the Delaunay triangulation. And I should just mention this other key tool is a piece of computational geometry by a computer scientist named Paul Chu. And so the work of Rafi and the work of Chu are sort of the crucial components to this measure estimate. I just like this story because I didn't necessarily expect I was going to be trying to read sort of CS computational geometry papers when I was trying to prove this L2 result, but there you have it. You never kind of know what you might need. Okay, I have about, I think, 20 minutes left. So let me now switch gears. Actually, maybe let me just stop and ask if people have questions about the translation surface part of the discussion. Okay, so now let me switch gears and let's go to talking about hyperbolic surfaces. Okay, so this maybe in some sense is even kind of more natural, but it's very natural that you could look at, for instance, the moduli space of genus G. So let's say now G is bigger than or equal to 2. Mg is the moduli space of hyperbolic surfaces of genus G. So, you consider surfaces with a complete hyperbolic metric, consider them up to isometry. And this is a nice space. Of course, there's some points where you have to be a little bit careful because the surface has a finite isometry group, but we're not going to worry too much about that collection of surfaces. And now the question, okay, you could ask all kinds of different questions. You have your favorite genus G surface. You could ask, oh, it's a hyperbolic metric. So what you've done is you've kind of thought of this as, maybe the hyperbolic plane wants some group, right? So gamma is isomorphic to the fundamental group of your surface, but you've nailed it down. That's what it means for me to have a hyperbolic surface. And you could say, for instance, you could say count geodesics, say closed geodesics. So now I see some folks from Warwick in the audience. This is, of course, something that they know very well. If you want to count closed geodesics, well, in the case of hyperbolic surfaces, it goes even further back. Maybe the history is here. Should be careful with the history. Maybe Patterson or I don't know. Mark, is there a right kind of person to attribute just accounting, the exponential accounting for hyperbolic surfaces?
Yes, Huber, H-U-B-E-R.
Huber, right. Thank you. Yes, it's too early in the morning to remember names. Exactly. So Huber proves that you have this exponential number of closed geodesics of length less than or equal to t. If I say n of sort of x is my surface, n of xt behaves like e to the entropy here. If you normalize it, let's say I can normalize it to the kind of 1 here. So e to the, or it's the gene, e to the, it's associated e to the ht over ht basically is the asymptotic growth with a co-volume number out front here. I'm not writing kind of the constant properly here. So this basically this should come from the growth of, it's course it's very closely related to a hyperbolic lattice point counting problem in the plane. And then, of course, many of us know this from the generalization to general manifolds of negative curvature in Margulis' thesis. And there's lots and lots of beautiful results in this direction where the count is now exponential rather than polynomial. You have lots and lots of closed geodesics. But you also have you could also ask a question. So before when we were counting saddle connections, I made the remark that the saddle connection was automatically simple. Most of these geodesics intersect themselves a lot. So instead, we're going to count simple closed geodesics. Okay, so let's call this, by slight abusive notation, I'm just going to call it, let's say m of xt is the number of simple closed geodesics of length less than or equal to t. So, if a geodesic intersects itself, I throw it away. Again, for probabilists, this is something, especially there's a big, wave in especially in sort of studying random walks and SLE. This is a concept that you guys like, right? Loop erased things. You don't want loops. And so here what we're doing is we're saying we're not allowing ourselves to cross our own path. So these are, in some sense, these are, I'm considering simple geodesics that don't cross themselves. So if you like to think about loop erased random walk, you've kind of already thought about something related to this. So Mary Rees showed that for a genus G surface, m of xt, there is constants above and below that you'll say C2, C1, t to the 6g minus 6. I should mention that this analogous result for saddle connections, the upper and lower bounds, that the fact that the number of saddle connections grows quadratically goes back to is a result of Masers. I don't think I mentioned that when I was talking about translation. So Mary Rees proved this, that the number of saddle connections of length, a number of simple closed geodesics of length less than or equal to t is on the order of t to the 6g minus 6. Lots of other people made important contributions, Igor Riven, Greg McShane, in various cases. But of course, as many of you know, the really, huge contribution happened, or the kind of resolution of this problem happened, where in Mirzakhani's thesis, where she showed that m of xt grows asymptotically like a constant, essentially a constant b of x times. I'm going to ignore, there's some other constants as well, but I'm going to kind of absorb them into b of x. Other constants that don't depend on x. And then there's this t to the 6g minus 6 figure. What is this b of x? This b of x is actually it's the Thurston measure of the set of measured foliations on the surface X with length on X less than or equal to 1. So measured foliations, maybe I'll call them sigma, with Lx of sigma, or sorry, yeah, L sigma of X less than or equal to 1. So what is the set of measured foliations? What is this notion of length of a measured foliation on a hyperbolic surface? Let me not get huge. Let me come back to that remark in just a moment. But let me first talk about where the random hyperbolic surface comes in. Suffice it to say, it's a function b of x that kind of depends sensitively on the geometry of the surface. But what about where's the randomness coming in? Where is the variance coming in? Mirzakhani also showed that if you integrate this function b of x over, there's a space, there's a measure called the Weil-Petersen measure on the moduli space that you get. This is not only less than infinity, she actually computes the number. She computes this number. Let me call it maybe b sub g, I think is what she calls it. And in particular, that's kind of a really remarkable result because it says if you integrate this counting formula over the whole thing, actually, and more than that, in a very similar way to Siegel, if you were to actually integrate the counting formula over the whole thing, any kind of asymptotics actually kind of disappears. You actually get this bgc to t to the 6g minus 6 plus. You get some lower order terms, but you get a polynomial in T. You actually get an honest to God polynomial in T here. Polynomial in T, and she can compute the leading terms of this polynomial. So not only do you get asymptotics for this, for the expectation of the counting problem, you actually get kind of exactly what it is. It's really a remarkable piece of work. Each time I encounter it, I'm kind of struck by how beautiful the answer to the story is. But in particular, what's interesting, let me tell you first, let me explain this in just a second, but basically, an analogy for us, b of x is an L1 of this mg Weil-Petersen. I should also mention, and I won't have time, I think, to discuss it in great detail, but there's actually a version of kind of a Siegel formula that Mirzakhani comes up with, where she says, start with a function on R plus, sorry, not contained in R plus, start with a bounded compactly supported function on R plus, then define f hat of a surface to be the sum of, or for all the curves gamma, where L gamma of x, of all the curves gamma, of f evaluated at L gamma of x, the length of gamma on x, and then she gets a relationship between the integral of f hat. She tells you if you integrate f hat dup, that it's the integral of f with respect to not now Lebesgue measure on R plus, but she identifies exactly what the correct measure on R plus is. So there is a version of kind of a Siegel formula that Mirzakhani comes up with that is crucial actually in her results. But it's okay, so a key point here is that b of x is an L1, but what is this measure? What is mu WP? Okay, so let me give a very quick and dirty answer that actually relies on lots of deep theorems. So what we're going to do is we're going to say, okay, well, how do I determine a hyperbolic metric? Well, what we're going to do is we're going to fix a Pants decomposition of the surface. So in this case, what we're going to do is we're going to cut the surface up along this curve, and this curve. And when we cut the surface up along these three curves, what do we get? We get we get two copies of something that looks like, let me kind of just draw it in this funny way. Actually, hold on, let me draw the red guys in there. sorry, this is a very bad drawing, but I think you guys kind of know what I mean. I get sort of these two thrice punctured spheres, right? These are supposed to be punctures on the surface of the sphere here. And I have to glue them along these red curves. So and now, for those of you who know a little hyperbolic geometry, once you specify the lengths of these boundary curves on a hyperbolic thrice punctured sphere, you completely determine the metric on these spheres. But now to glue them together, I have some twist parameters. So to each of these circles, I have a parameter, let's say L1, tau 1, L2, tau 2, L3, tau 3. The LIs are in kind of R plus, and you can always sort of take the tau i's to be kind of between 0 and Li, very broadly speaking. These are called Fenchel-Nielsen coordinates, and you should stop and say, wait a minute, aren't there lots of possible Pants decompositions on surfaces? And the answer is yes, there are. So when I say Fenchel-Nielsen coordinates, it depends on the Pants decomposition that I fix. And now I'm going to make something even more irritating. I'm going to say that what mu WP is essentially DLI wedge d tau I. It's just you just multiply. It's just basically DLI wedge times d tau I. It's you just multiply all of these guys together. So it's just DL d tau. And you might say, wait a minute, that's also ridiculous, because you just told me that these coordinates are ambiguous, that you have to specify the Pants decomposition. So what's really hiding is a theorem of Wolpert here. You can define the Weil-Petersson metric. Technically, the Weil-Petersson metric is defined using the Weil-Petersson symplectic form, which comes from an inner product on the tangent bundle, or you can find it on the cotangent bundle, and you define a volume. You take the wedge product of this symplectic thing, and you get the volume form from it. But Wolpert showed that this is true. That this maybe I'll say this, whatever is in green here, is true. Right. So this I should really be very clear. Wolpert's theorem is very hard and very deep. It's a really remarkable and beautiful result. Okay, so now I think you probably by now know what we're going to ask. The question is B of X? So this is something that now I think is more and more, I'm calling it, and we're trying to get people to call it the Mirzakhani function. Is it in L2? And if you kind of carefully trace what's in Mirzakhani's work itself, Mirzakhani shows it is in L2 minus epsilon, and it is not in L2 plus epsilon. It is in L2, so B of X is in this, B of X is not in L2 plus epsilon for every epsilon positive. She didn't write it down as a statement like that, but you can find it in her work. So now the question is, but that still leaves the question, is it actually in L2? Does it actually have finite variance, right? We all know you can build things which are right on the edge. And so the last theorem I want to state is a recent theorem of myself and a very bright young graduate student at Stanford, Francisco Arana-Herrera, who's on the job market this year. So we proved, in fact, that B of X is in L2, not X here. And what we don't just prove that. We prove this by essentially showing that the estimates. So what you need to understand here is you need to understand now the behavior of this function near the boundary. So one of the common threads in all the problems I've been talking about is, of course, that these underlying spaces are non-compact, right? That's why we can have interesting functions that blow up, and these interesting functions blow up near the boundary, and you have to control the behavior near the boundary. In particular, we need to understand curves when the surface itself might have a very, very short simple curve. And again, it's kind of spiritually similar to the work with Masur and Cheung, where we have to say, okay, well, how can we have lots and lots of curves? There's certain pictures that allow that. And we have to control the measure of those pictures. And in fact, Mirzakhani had done a bunch of that work for us. And what this involved was sharpening some, in just a very small way, a couple of results of hers showing she had bounds on the B of X, that showed this, and showing that the bound, that we were actually closer to kind of the L2 minus epsilon bound. And that was kind of good enough to getting us L2 plus L2. We were closer to kind of the upper bound rather than the lower bound near the boundary. So it's just kind of a careful analysis of some work. I should mention this result has corollaries on counting problems for pairs of curves, the kind of correlation between curves. And I have to say, and I can say this because Francisco very nicely did a lot of the writing of some of these sections, that it's actually very well written and very easy to read. And if you actually want a brief introduction to the relevant parts of Mirzakhani's work, you can look at our paper as well. So this is all of this is published. And so now there's I think more interesting questions here, which is, for instance, so a couple of very interesting to me, and I think quite difficult questions that are wide open and kind of naturally implied by my talk. So one is just going back to the setting of flat surfaces. It's compute integral of f hat squared d mu over h1. So give a formula for it. And then similarly, compute integral of b of x squared d mu over mg. And when I say compute here maybe I actually want a formula. Here, maybe what I want is some kind of behavior as g goes to infinity. Both of those things I think would be extremely interesting. And I think, integral of b of x squared, probably one can recover from some parts of Mirzakhani's work, but I think there's a lot of interesting work to be done there. So I think this is maybe a natural place for me to stop. And again, thank you guys for your attention over 3 weeks, and especially, for letting me talk for 3 full hours. I appreciate it.
So thanks, Jayadev. That was a lovely series of talks, very interesting. Are there any questions for Jayadev?
Since there aren't questions, let me actually share one other question, especially that pops up to this, is there's other models of building random hyperbolic surfaces, or even random flat surfaces. You could build them more combinatorially. I think I mentioned this at the start of the first talk. You could take some polygons and do some gluing with some, say, permutation. And you could ask some of these similar questions for those kinds of constructions. What is the expected number of simple closed curves? What is the variance? And a lot of those probability distributions are kind of compactly supported. So you would get, actual numbers, but you might ask them some limiting procedures. You might say, could I do these computations of these f hat squared or b of x squared by taking limits of kind of finitely supported probability measures that limit on to these things? And I think that's a question that would be very interesting, and it would be very good to get some probabilists involved. Because if you can approximate these measures by kind of finitely supported measures built by some combinatorial construction, that would be extremely interesting. So for instance, another well-known combinatorial construction of random hyperbolic surfaces is by Brooks. So there's lots of interesting, I think, questions in this direction. Braun Petrie is someone who works on these questions, and there's lots of interesting work happening. I should just advertise briefly, actually, in an hour and a half, there's a talk in the Bistro seminar on random hyperbolic surfaces by Laura Monk that looks very interesting. So if you're interested in this material, you can shoot me an email, or you can Google Bistro seminar and find the Zoom link for that 10 o'clock talk.
So there's some questions in the chat.
Yes, Nishant, yeah. So yeah, our proof does prove that we prove that it's actually an L2 plus a function depending on genus. That function depending on genus, I'm not sure whether it's optimal or not. In fact, I sort of have a suspicion that in fact it might be an L3 minus epsilon in the translation surface setting, but we don't have a proof of that.
Excellent. So if there are no further questions, let's thank Jayadev again for this lovely series of talks.